All right, next I want to look at Chapter 13. And we've already looked at Chapter 13 in a little detail before when we did circular motion with the gravitational force. But there are a couple other things I wanted to look at that relate to escape velocity and also the potential energy for a spherical mass. In order to make sense out of this, we're going to need a Chapter 7 result, which is also a subject I haven't covered yet, but I want to cover it right now. And that's the fact that, in general, we can relate the force to the potential energy function, if that potential energy function is a function of position. And so if we could plot, for example, the potential energy function, let's say it's a parabola, u versus x. Let's say this is a one-dimensional problem. Then we could write the potential energy function as 1/2 kx squared, which should be the potential energy function for a simple harmonic oscillator. Now what this relationship tells us, f equals minus du dx, is that if you were to take the slope of this curve and then change the sign on that, what that would give you is the force function. And so if this is x equals 0, that's our unstretched length of our spring, and then we pull at a certain distance a away, like this, then we're going to get a restoring force which is negative, and that force is equal to minus k. We call this x naught if we want. And so we can see that this slope is equal to kx. But if we change the sign on that, that force function is equal to minus kx at this point, which is just the negative of this slope. So let's see if that works over here. Let's see if we can get Hooke's law by taking the derivative of u with respect to x. So d by dx, that should be our Hooke's law spring relationship of 1/2 kx squared with a negative sign out in front because it's minus du dx. Sure enough, gives us minus kx. So this works. And it works for any potential energy function where the force is related to u. Now what if you had forces acting in 2 or 3 dimensions? Well, then this would be a partial derivative of u with respect to x for the x component of the force, a partial derivative of u with respect to y for the y component of the force, and similarly for the z component. For our problems, though, we'll just be dealing with functions of a single variable, so you don't have to worry about partial derivatives for our applications, either in Chapter 7 or Chapter 13, or for the midterm. Okay, so that's the kind of relationship we have. If this thing were to compress to its point of maximum compression, then we'd be at minus x naught here. And then at that point, the force would be still minus kx, but it would be pointed in the positive direction. So this is a negative slope, but the negative of that is a positive slope. So that gives us the positive value for the force as it goes back and forth between plus or minus x naught. Now, what if the potential energy function is just a function of r? Well, that turns out to be the case if we want to know what the potential energy is a certain distance r away from a spherical mass. Potential energy at this point, a distance r away, let's call this little r, and this big R will be the radius of the planet. R is greater than big R, is equal to minus g times the mass of the planet divided by the radius of the planet. And here R is greater than the radius of the planet. And so that's a different expression from what we looked at before. Before we saw that the potential energy is mgy if we're close to the Earth's surface. So that delta PE was equal to mg times the change in the height. But the problem with this is that g is a constant. So in other words, this potential energy expression, which we're also calling U now, U for potential energy, is only good when we're close to the Earth's surface. So we need a different expression for the potential energy for a spherical mass. Now I just stated this was true, where m then is the mass of the planet. And r is the distance from the center, not the distance from the surface. But how do I know this is right? Well, I do know what, if I put a mass here, I know what its force relationship is. Okay. And so if I take this relationship and I turn it into, actually this should be times the mass of the particle, because what we want here is the potential energy of a particle and not just the potential without the particle. So make this minus g times the product of the masses divided by r. Then if we want a force relationship, we know that that's equal to minus g big M little m over r squared. That's our inverse square law. Now, how do I know that's negative? Well, because the force is in the opposite direction from the direction of increasing radius. So the force then is a restoring force that tends to bring little m closer to big M. So little m is the mass of the object. And so what I want to try to do here then is to get this relationship from this one by applying the F equals minus du dr relationship. So let's do that. Let's try that. We'll do that over here. And that will be minus d by dr now. Okay, d by dr. Because now we're talking about the force as a force of radius of minus g m little m times r to the minus 1 power, or minus 1 over r. Okay, so this minus will cancel out that minus. That'll just give us g big M little m times minus 1 times r to the minus 2 power, or that's just equal to minus g big M little m over r squared, times some unit vector that points in the r hat direction. Okay, so that's exactly what we're looking for, is something that satisfies our Newton's inverse square law relationship when we take the derivative of u with respect to r. And so what that shows is that instead of using a potential energy term that looks like mgy, where g is going to change. We know that's going to change as we get farther and farther away from a mass. What we're going to use instead is this potential energy expression. But it's negative. And I told you before that I don't like negative potential energy, so why am I using it here? Well, because if we plot u versus r, it looks like this. And so for a certain distance away, this u value here is going to be minus g big M little m over r. But I can still increase the potential energy by going a farther distance away. And so delta U here is still greater than 0. So that corresponds to an increase in the potential energy, even though I'm making it less negative. So the biggest that you can get is 0. When r equals infinity, U goes to 0 as r goes to infinity. But since it starts out negative, we can still increase U. Delta U is positive as R final becomes greater than R initial. And so that means that this works just as well for adding up potential energy, because we're getting a positive change in potential energy as we move the mass farther away. But here it's just making it less negative rather than making it more positive. Now why are we doing that? Well, because if we wanted to have this be a positive value for U, we'd have to add an extra term here in order to set it up, say, as being 0 at the surface of the Earth. And mathematically, that's a much more difficult process to keep consistent with the equations. And so this gives us the simplest equation that we can write without having to get a bunch of artificial zeros imposed by adding other correction factors into our expression. And so even though it may seem a little bit obscure to have the potential energy always be negative, remember it's changes in potential energy that are really important, not the potential energy itself. And so the changes can be either positive if you're moving farther away or negative if you're moving toward, just the same as they would with our mgy term. So with that thought in mind, let's go to a spherical planet problem in which we've got a rocket ship, say, on the surface of the Earth, and the radius of the Earth is equal to 6,370 kilometers. The mass of the Earth is equal to 6 times 10 to the 24 kilograms. And let's say that we want to fire this rocket at such a speed as to achieve escape velocity. Let's find the velocity at the Earth's surface that will allow the mass to escape to infinity. So in other words, achieve escape velocity. That's what we really mean when we say escape velocity. Okay, and so what is escape velocity? Well, it's just the speed, the minimum speed that we can give this thing at the Earth's surface. We'll call it v escape, so that it just makes it to infinity with 0 extra velocity. So we have no extra velocity when r equals infinity. So that means the mass just escapes, but with 0 velocity to infinity. And then we have escape velocity. Okay, so this concept is important. Even though a mass is never going to quite get to infinity, we can still use this to say, how fast do we have to get this object going so that it will escape the influence of the gravitational pull of a given planet. It doesn't have to be the Earth. So what we need then is an adapted version of the energy equation. We can say that 1/2 times the mass of the rocket times v escape squared plus the potential energy, which is minus the g times the mass of the rocket times the mass of the Earth divided by the radius of the Earth. Okay, so that's its initial potential energy when the rocket is standing on the surface of, sitting upright on the surface of the Earth. And it's just going to be g times mass of rocket times mass of the Earth divided by the radius of the rocket. Equals the final kinetic energy. Well, this is at infinity. V equals 0 at r equals infinity. So the kinetic energy term is 0, plus the potential energy term, which is minus g times the mass of the rocket times the mass of the Earth, divided by infinity. G m1 m2 over r. You divide by infinity, that also gives you 0. Okay, so that means that the kinetic energy and the potential energy are 0 to begin with, and they're 0 afterward. So if 0 equals 0, what good is this? Well, you can still solve this for the escape velocity, because you've got this term plus that term equals 0. So if we bring this term over to the right-hand side and solve for v escape, we get that v escape squared equals 2g me over re. We notice here that the escape velocity does not depend on the mass of the rocket. That's going to cancel out of this equation. And so therefore v escape is just the square root of 2g times me over re. And so if we plug in values for that, using the universal gravity, remember this is big G, not little g. Big G is the gravitational constant, and that is equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So plug that in. We've got the mass of the Earth and the radius of the Earth already. So this is square root of 2 times 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by the radius of the Earth. Now here we are given it in kilometers, so 6370 times 10 to the 3 meters, that's RE, because this is 6370 kilometers, or that's 6.37 times 10 to the 6 meters. Okay, so that'll go in down below, 6.37 times 10 to the 6 meters. That gives us 1.1 times 10 to the 4 meters per second, or that's equal to 11, this is 1.11, 11.1 kilometers per second. So that's our escape velocity. Now this is roughly 8 miles a second. So if I don't have air resistance, and of course we're removing air resistance from the calculation, and I throw this thing up at a speed of 8 miles per second, it can just escape the Earth's gravity and then slowly slow down until by the time that it gets all the way out here to infinity, it just comes to rest at infinity. And that's how fast we would have to make it go for that to occur. Okay, so that allows us then to determine the escape velocity from our modified form of the energy equation. And now let's try another example. In this example, let's say that we start out with half the escape velocity. And here we're assuming the rocket doesn't fire after the initial blast. So it could just as easily be fired out of a cannon. Okay? So this is not something where the rocket engine is still working continuously through the process. But let's say here that the initial velocity is equal to 1/2 of the escape velocity. If V naught is equal to 1/2 V escape, let's find R max for the rocket. So let's, actually here, I think this will work out better if we make this 1 over √2, the escape velocity. So let's do that. Let's find R max for the rocket. In other words, how far does the rocket go before it turns around and starts to come back again? Okay, so if we plug in here, we see that we've got 1/2 mass of the rocket times 1/2, or 1 over square root of 2 times V escape squared. Minus G, mass of the rocket, times the mass of the Earth, divided by radius of the Earth, equals, now we want the maximum R value, so we reach R max, V final is 0. So that means we have no kinetic energy at this endpoint. So V final is 0. And the potential energy is what we're going to want to solve for, which is minus G mR me divided by big R. So that's what we're going to want to solve for. Here we have V escape. So 1/2 of V escape squared is just going to be equal to 1/2 times mR times G me over R. Okay, because V escape is the square root of 2 G me over R. And this is 1 over the square root of 2. So that just squares that, but with the 2 taken out. Okay? And then we'll subtract from that G mR me divided by RE. Okay, so this is 1/2 minus 1 equals, over here, minus G mR me over R. So do I even need G and mR and me? Well, no, because they all cancel out of this expression. So when I cancel all of these out, what I end up getting is 1 over 2 RE minus 1 over RE is equal to minus 1 over R. Or this is like minus 2 over 2 RE. So this is minus 1 over 2 RE equals minus 1 over R, or R equals 2 RE. So in other words, with 1 over the square root of 2 times the escape velocity, that's 0.707 V escape, or 70% of the escape velocity, we end up only at a distance of 2r away from the center. Now if it's 2r away from the center, then that means that it's 1 Earth radius above the surface. And so that would be the way then to handle a problem like this. If we were given what the initial velocity was and we wanted the maximum distance that the object was able to reach before running out of kinetic energy. Now, back around the year 1800, a guy looked at an expression like this one for V escape, which we saw before was the square root of 2 g m of the planet, whatever that was. Let's just call it m for the moment because it'd be something else, where r is the radius. This could be a star if you wanted, and this could be the radius of the star. It doesn't have to be a planet anymore. But if you were at the surface of this thing, you would need this amount of velocity in order to escape to infinity. And so what did this guy do with this? Well, he said, well, what if we set v escape equal to the speed of light? So this scientist then proposed a existence of a dark star. If v escape was equal to the speed of light. Because at that point, light couldn't escape from the star. And so he said, well, then the star would just be dark. And so this, of course, is the condition now for what we call a black hole. But way back in 1800, this guy came up with this relationship. Amazing kind of foresight. And so if we set then v escape equal to c, then basically what we could do is solve for the radius of this dark star, which would be the radius of a black hole. Pretty cool. And so that's what he did. He set the escape velocity equal to c. That's the square root of 2g times the mass of that central object divided by the radius. Okay. And then if you solve this for the radius, r, what you find by squaring both sides of this equation is that r is equal to 2gm over c squared. And so what we know now is that this is the expression for the radius of a black hole. Okay, and so let's see then, they've wondered at the Large Hadron Collider whether or not the Earth is in danger, because they've speculated that if you collide particles with a high enough velocity, you might be able to create little mini black holes in the Large Hadron Collider. And if that happened, then what if those little black holes started to gobble up more and more matter and eventually swallowed the whole Earth? How big would the Earth be if that were the case? So let's not worry too much about whether this is really going to happen or not. But let's just ask if somehow the Earth turned into a black hole. How big would it be? Now, what is a black hole? Well, essentially, it's a star that's been smashed to zero size. And so we believe that there are, in fact, many black holes out there in the universe. And they're some of the most interesting and mysterious objects in science. And so let's go ahead then and see how big the Earth would end up being if it was turned into a black hole by one of these little mini black holes that kept gobbling up more and more matter and eventually gobbled up the whole Earth. So we write this then as 2 times g, 6.67, times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by c squared. So that's 3 times 10 to the 8 meters per second, quantity squared. That gives us 0.88 centimeters. Or 8.8 millimeters. So if you smash the Earth down to the size of a black hole, it'd be smaller than a marble. And so a lot of people are saying, well, Large Hadron Collider shouldn't be doing this because that's pretty risky to endanger the entire planet just for scientific curiosity. But my answer to that would be there's a possibility of 2 Nobel Prizes here. You could show, first, that there are extra dimensions, because you won't be able to make a black hole unless we believe there are a larger number of dimensions than we can spatially perceive. And of course, you get a second Nobel Prize for creating the black hole. And so, for me, it's a no-brainer. Don't you think that's worth the risk?